Good afternoon, ladies and gentlemen. I am Máté Péter Tóth. I'm in my first year of electrical engineering of bachelor degree. This is my partner, Katherine Cazco. Arguello.
Good afternoon, everyone. My name is Katherine Cazco. I am studying master in electrical engineering, and today we will present in the footprint of the ISS. But
before we start, let me ask you a question. Do you know which is the uninhabited island where your closest neighbor will be an astronaut? We will answer you this in the end. Our content will be about the introduction, the theoretical framework, about the background of the whole work, about the International Space Station, radio communication planning, methodological framework, system design, communication, tracking system of the Earth Station, free space attenuation, calculations, and in the end, our results and our summary.
Today we will speak about how to establish communication between the ground station in York and the ISS for communicating in the future with Hungarian astronauts. Next. In the background, this project has become feasible due to presenting projects. The first presenting project was EME Air Moon Earth, where we arrived the first giant antenna 4x12, and the second project was the base station ACA, where we arrived the 4x19 giant antenna.
The International Space Station is the largest human-made object in space. It is orbiting on LEO orbit. Its maximum height is 412 kilometers. Mostly space research is conducted here. There are even times when the personnel on board are making calls with Earth stations located on Earth.
In the radio communication planning, first we need to know the footprint. The footprint are the regions of the Earth's surface encompassed by the signal transmitted by a satellite. In the case of ISS, the footprint is 4,221 kilometers, and the ISS is into the LEO orbit. And then we need to know the frequencies that we need to communicate. We use the bands from E2, the band 8, with very high frequency, and the band 9 with ultra high frequency.
As we have spoken about it before, we will need to use two different frequencies. This is why we don't only have one radio and one antenna, but we have two antennas for both uplink and downlink. This way we can make it possible to communicate with other satellites also, and not only the International Space Station.
In the system of communication, first we have our transceiver equipment, that is radio AC 9700 with an output power of 100 watts in FM. Then we have two giant antennas. The first giant antenna uses the radio amateur band 144 to 146 MHz for uplink and with a wavelength of 2 meters, and the second giant antenna uses the radio amateur band of 430 to 450 MHz with a wavelength of 0.70 meters. Also, we use coaxial cable. Then in the ISS, they have a Kenwood TMT710E radio with an output power of 50 watts. Also, they have a set of 4 UHF antenna system to support the existence of this radio Kenwood. And for the communication with ISS, we used for uplink for 145.9 MHz and for downlink 437.8 MHz.
The tracking system of our Earth station looks like the following. And why do we even bother with tracking system? Well, since we have to reach the space station, we have to use good antennas for good link. And these antennas must be rotatable, just to face the right way. This is mostly done automatically by gpredict, with downloaded TLE files from the network. We only have to select our needed satellite, or in our case, the space station itself, and it will follow it for us. This program is pre-written for us in Node-RED, which translates the signals for our PLC controller, which then sends the rotators the signals to rotate the antenna themselves.
Then we have the free space attenuation. The free space attenuation is used to calculate the attenuation of signal strength between two antennas. So we have two antennas. The first antenna is for uplink and the second antenna is for downlink. And we do our calculations with a distance of 412 kilometers when the satellite is just above us. Next, please. We use the formula from E2, that is 32.4 plus 20 logarithm, the frequency for uplink, plus 20 logarithm, the distance in kilometers, plus 3. This 3 bit is, for example, atmospheric attenuation, polarization attenuation, or humidify. And we calculate for uplink, that is 130.97 dBs, and for downlink, that is 140.52 dBs. Next. Another factor that influences the communication is the Doppler effect. This involves the variation of the wavelength of any type of wave emitted or received by a moving object. With this formula allows to calculate the maximum frequency shift respect to the carrier frequency emitted or received by a satellite. So with this formula, we use the frequency for uplink and downlink, the speed of the light, and the speed of the satellite. In this case, the speed of the ISS is 7,777 meters by second. And we found the values that you can see here in the slide. But generally, to work in amateur radio satellites in VHF, the Doppler effect is around plus minus 3 kilohertz, and in UHF is around plus minus 10 kilohertz.
We have made multiple noise level measurements, both on roof of the building D and on the top of the Radio Amateur Club. These are our measured noise levels. We use the bandwidth of 2 megahertz. We made the measurement for the whole radio band, amateur radio band. We also made noise calculation for the ISS, since they don't have the same noise as we have down in Earth. It uses the Boltzmann number, the thermal noise, and also the bandwidth. We also made link budget calculation. As you can see, we have our transmitting power of 2 decibel watts of our IC 9700 radio, and this signal is sent with our transceiver antenna, which has the gain of 15.45 decibels. Of course, this link is getting worsened by the free space attenuation with its value of 130.97 decibels. And also the ISS receives it with their antennas, and then the radio receives its signals, and this radio has the radio the ISS uses has the sensitivity of minus 163.8 decibel watts.
Then, for the calculations of the link budget, we use the formula for the power signal. That is the gain on the transmitter, the gain on the receiver, the power of the transmitter plus 20 logarithm the wavelength by 4p the distance. So we know that distance is 412 kilometers. We know the gains of the transmitter and receiver. For uplink, we have a power signal of minus 87.76 dB watts, and we calculate the signal to noise ratio with the power signal minus the noise measured in the satellite, and we obtain the value of 99.08 dBs. And the same we calculate for downlink with the signal to noise ratio, the power signal minus the noise measured in the top of the dormitory, and we got 54.8 dBs.
There are multiple aspects to choose a location, or the right location. There is the noise level, visibility, and indoor equipment placement. We could have chosen from two options. One was the top of the radio club, and the other was the roof of the building. And the top of the radio club was chosen because it has much less levels of noises, and this way better quality of radio calls can be made.
In the implemented station structure in the top of the college, we already have our radio equipment. We have the two giant antennas. We have the camera to view the movement of the antennas. Also, we have the elevation azimuth controller G5500. Also, we have the system to automate the rotor of the antennas. And we have the computers with the softwares that we need, for example, GPredict. Next.
We have made tests with satellites before the ISS itself, since the ISS doesn't always come when we would like to see it or we would like to talk through it. We made tests with the SO50, with the RS-44 and with the AO-85 satellites. These satellites work in single sideband, not in FM. However, they work the same way, almost the same way as the ISS do. They have almost the same uplink frequency and the downlink, almost the same downlink frequency to use. With these tests, we made multiple connections. This way we knew that when the ISS comes, we can talk through its repeaters.
In the test with ISS, we captured the signal from ISS when they were transmitted for responding some questions of children in a special day. So we hear of ISS in 3 occasions when they passed through our orbit, and the connection was very clear.
Our summary is that the noise level of the top of the college is much more smaller than in the roof of D. I haven't told you, but the roof of the radioamateur club is on top of the college. Yagi antenna has the best size and stability for the wind for us, since on top of the college we don't have much space to use parabolic antennas. It is possible to make a connection, and we made successful transmissions with other satellites also.
And we made successful transmissions with satellite, especially with SO50 satellite. We made 9 successful connections, which has a much lower power signal than ISS. Also, all tests with ISS was successful, proving that our calculations were correct. And we continue our work because we want to create a duplicate ground station without any unexpected error.
With the work, with the connections, we had the first one in November 15 in 2023 with an Italian Earth station and with also a Spanish one. We have made with England also and with Austria, and we haven't noted the other ones since we were making further involvement. And we had our first communication through ISS with another Hungarian Earth station on November 20th. This Earth station was located in Kapuvar, roughly 50 kilometers away from Győr. It would have taken only 50 kilometers for the signal to reach each other, but we talked through the ISS itself, almost 800 kilometers. And before we finish our presentation, I would like to thank everyone who made this work possible. Most importantly, Lajos Kéri, who was showing us the ropes and leading us into the work of working with the ISS's repeater, the Honfi Radio Amateur Club, and also the dormitory for letting us using the dormitory's place for this whole operation, and also the University of Győr, of course. And köszönjük szépen a figyelmet!